Hello, everyone. Thanks, Dan, for the warm welcome. So today, I wanted to talk about quantum computing and how it's actually part of the future of mobility. So this is a very complicated topic, but I'll start with some basic things. Essentially, I wanted to discuss something that I'm very passionate about, which is quantum computers, and we'll get to that in a second, and something which I'm a bit less passionate about, which is traffic. And in fact, let's call things like they are. Traffic sucks, right? I don't know if there's anyone here who likes traffic. I can bet there's probably no one. And there's a very simple reason for that. First of all, traffic affects us all, right? It's a problem that concerns half of the world population, which currently lives in cities. And because we lose a lot of time because of it, approximately, if you live in a big city, like a capital or any larger city, in any country around the world, you'll lose more or less 8 hours every single week, every single month. And there's also a big health concern. If you live in those cities and you walk around, there's probably a lot of smog and a lot of pollution going on, which is mainly caused by traffic congestion. So one of the big questions that we're all asking here, and that's why we spent those 2 days here in Katowice, is how can we solve it? And one of the most, I would say, sought after, hottest topics in traffic optimization within that field is the concept of global optimization. So what really is global optimization? So it's an assumption that in a world where you have autonomous vehicles, where you have connected vehicles, we have sensors, smart cities, and you have so much data and so much connectivity between all the actors in traffic, they can actually use that information to optimize routes for all the vehicles in a given system. So if you kind of imagine a scene from Minority Report and a highway where every car moves autonomously at the same speed, not too fast, not too slow, that's pretty much what we're looking at. But there is a very serious problem complexity around it. Because if you imagine that you have 10 cars, and for those 10 cars, you have 3 routes that are possible, then this gives you 10 to the power of 10 of combinations that you could have. So that's approximately 60,000. So that's okay. But if you have 30 cars, or 20 cars, that's already 3.4 billion. If you have 30 cars, then that's already 205 trillion different combinations. So those problems get very quickly become very complex. And that's not anywhere near the real-world problem that we have, because you have 4,000 buses in Paris, you have 13,000 taxis in New York City, you have 2.56 million cars in London. So the real-world problems that I actually need to solve are much more complex. And that's why we need a powerful optimization engine. And that engine is a quantum computer. So moving to the second part of what is the more complicated side of the things, what the hell is a quantum computer? So for the past 70 years, we more or less had the same approach towards computing. We went from vacuum tubes to microprocessors, but the principles of computation have stayed pretty much the same. And they all have been relying on one invention, which is the transistor. So that thing was invented in 1956 by a company called Bell Labs, and it's the very first transistor that has been ever created. And a transistor has a very simple principle. It lets electricity go through, and then it gives you a 0 or a 1, right? And if you put all of those zeros and ones, then you can have a very big computer, which allows you to do very powerful computations. And the reason you're able to put a lot of those transistors is because those transistors have become smaller and smaller. So this is something called Moore's Law, which says that every year we more or less double the computing power because we double the number of transistors, which is due to the fact that we're making them smaller. So in fact, as of today, a single transistor is between 5 and 15 nanometers. And that's approximately 4,000 to 5,000 times smaller than a human hair. And because of that, we are more or less reaching the limits of how much smaller those transistors can actually become, right? Because there is a certain physical limit as to how much we can be scaling the computing power by making transistors smaller. So in fact, quantum computing is this new generation of computation, which takes advantage of a completely new paradigm. It relies on quantum physics, it relies on inventions that are, I would say, fairly old, come from the 30s, 40s, and 50s of the past century, but haven't yet been fully explored in terms of using them for computation. So obviously you have superposition entanglement, which are 2 core fundamental laws of quantum physics, which are used to make more powerful calculations. And instead of bits that you have in classical computers, we use qubits. And the computations that are being done by quantum computer, instead of being deterministic, always a 0 or a 1, are probabilistic. So you can have either a 0 or a 1 or any value in between, depending how you treat the machine. And one of the great uses of quantum computing is optimization. Solving complex optimization problems, like the ones we mentioned for traffic optimization, is one of the best use cases that a quantum computer could be used for. So in fact, if you imagine a quantum computer, and if you compare it to a classical computer, the potential that you will have for solving optimization problems will be greatly increased by taking advantage of the quantum physics and by taking advantage of the probabilistic nature of the machine. So in fact, if you look at the future of traffic optimization, the idea of making global optimization possible relies on the fact that at the very bottom you will have traffic. You will have cars, you have buses, our roads, everything in a system that is very connected thanks to the IoT devices that we have. On the top you will have a quantum computer which can be used as a powerful engine for solving very complex optimization problems. And somewhere in between you will have a set of algorithms and software which can be used to translate all the data and translate the optimization problem coming from traffic to something that a quantum computer can process. And that's also a very complicated task, because due to the new paradigm that is being used in computation, you have to develop new algorithms and new software that actually rely on completely different rules than classical computers. And this is something that we're working at our company. We have developed and are continuously developing a solution called the BOHR solver, which basically does what I just said, which translates a classical optimization problem, a very complex one, and translates it into something that can be computed on a quantum computer. And hopefully, we expect that in the future our solution will be part of traffic optimization, will be part of the solution for solving traffic congestion, and could be also applied in many other industries. So hopefully, you'll become advocates of quantum computing, and you will see the importance of it for the future of traffic optimization and solving traffic congestion. And if you're looking for more information, are welcome to join our website and have a productive discussion as to how we can change the future of mobility by using quantum computers. Thank you.